Imagine, if you will, a scenario. It feels a bit like a thought experiment from a philosophy class, or maybe the opening scene of a sci-fi thriller. You have the world's smartest genius locked inside a room.
A very specific kind of genius, though.
Exactly. Let's really paint the picture here for everyone. This isn't just a smart person. This is someone who has, read the entire internet, every book, every line of open source code, every Wikipedia article, every Reddit thread, but only up until a few years ago.
Right. They are frozen in time. A snapshot of human knowledge from, say, 2021.
And they're locked in this room. It's a steel room, no windows, no Wi-Fi. You cannot go in. You cannot send a brain surgeon in to rewire their neural pathways or add new memories. You can't just sit them down and explain what happened in the world last week. The room is hermetically sealed.
The ultimate black box.
That's the term. And the only interface you have is this tiny little slot under the door. You can scribble a question on a piece of paper, slide it under, and a few seconds later, this genius slides an answer back out.
And usually those answers are incredible. I mean, they can write sonnets, they can debug Python scripts, summarize the entire history of the Roman Empire. They're articulate, they're logical.
But, and this is the giant but that really drives our whole conversation today, there is a fatal flaw. If I ask this genius about something that happened this morning, or if I ask them to analyze a confidential legal contract that is sitting on my desk right now, a document they have never seen, they fail.
They have to fail. Right. They just don't have the information. It's not in their memory.
They either say, I don't know, or, and this is even worse, they vividly hallucinate. They just make things up because their brain, their fixed neural weights, it tries to complete the pattern based on old data. So they might confidently tell you the CEO of Twitter is still Jack Dorsey, or they might invent a clause in your contract that doesn't exist at all.
Because you can't open the door.
Yeah.
You can't just teach them new information in the traditional sense of learning. You are stuck with the brain you have.
So the mission for today's deep dive is really solving this locked room mystery. The question is, how do we teach this old dog new tricks when we are strictly forbidden from touching the dog's brain? How do we take a frozen, inaccessible genius and make them smart about today?
It really sounds like a paradox, doesn't it?
Uh-huh.
But it is actually the specific problem solved by the paper we are unpacking today. It's titled REPLUG, Retrieval-Augmented Black Box Language Models.
REPLUG, retrieve and plug. It sounds a bit like a hair loss solution or maybe a plumbing service, but I promise you listening, it is so much more interesting than that. This is about a fundamental shift in how we think about building AI systems.
It really is. It's about moving from trying to build a bigger, better brain to building a better way of feeding information into that brain. It's a shift from being model-centric to being more data-centric.
Okay, let's unpack this. The mission for this deep dive is to strip away the complex mathematics. And having looked at the paper, there is some heavy calculus and probability theory in there, and we want to look strictly at the methodology. We want to understand the architecture of how you combine a frozen, untouchable supermodel with a smaller, agile, trainable librarian to create a system that is smarter than the sum of its parts.
That is the goal. And honestly, this is relevant to anyone using AI today because most of us are using these black boxes whether we realize it or not.
Let's start right there then. We keep saying black box. In the context of this research, what exactly makes a model a black box? I think a lot of people might assume, oh, if I use an open source model, I can see the code, so it's a white box. But that's not quite what we mean here, is it?
No, not at all. That's a really important distinction. In the AI research world, we distinguish between white box and black box based on your level of access. A white box model is one where you, the researcher, have the keys to the kingdom. You can see the specific weights of the neurons. You can see the gradients.
Gradients. Okay, give us a quick, non-math major refresher on that term.
Sure. Gradients are essentially the mathematical directions the model uses to learn. So when a model makes a mistake during training, the gradient tells the math which way to adjust all the little numbers inside to fix that error for next time. If you have the gradients, you can train the model. You can fine-tune it.
Okay, so this is like working on a car with the hood up. You can actually get your hands greasy. You can tighten the bolts on the engine yourself.
Exactly. If the car isn't running right, you can tune the engine components directly. But the most powerful models we use today, GPT-3, the models powering Copilot, the massive APIs from companies like Anthropic or Google, these are all black boxes to the end user.
You send text in, you get text out.
And that is it. You have zero visibility into why the model made the decision it made. Structurally speaking, you certainly cannot change the weights. You can't reach inside and say, hey, focus more on this variable.
So if I'm a company and I want GPT-3 to know all about my specific internal HR policies or my secret product roadmap for 2027, I can't just, download GPT-3 and fine-tune it on my laptop.
Well, there are two huge reasons for that. One, you simply don't have access. The companies just won't give you the weights. But two, even if you did, let's say you're a billionaire and you buy the model weights, fine-tuning a 175 billion parameter model is astronomically expensive.
We're talking about more than just a good gaming PC.
A little bit more, yeah. You need dozens, sometimes hundreds of high-end GPUs like A100s or H100s just to load the thing into memory, let alone run the backward passes required for training. We are talking about millions of dollars in compute time. It is completely out of reach for, what, 99% of organizations?
So we are stuck with the black box. We have the genius in the locker room. Now, usually the workaround for this is something we've talked about before on the show, RAG, Retrieval-Augmented Generation.
Right. The standard RG approach.
And the standard way is pretty simple, isn't it? You find the relevant text, say your HR policy document, and you just paste it into the prompt. Hey, genius, here's a document. Read it, and then answer my question.
That's the classic method. It's called concatenation. You just append the document to the input.
But the paper highlights a major flaw with this just paste-it-in strategy, the context window.
It is a massive bottleneck. I mean, even as context windows get larger, we're seeing 32K, 100K, even a million tokens now. They aren't infinite. And more importantly, models get confused.
Confused how? Like, what does that look like?
It's a phenomenon researchers call lost in the middle. If you take, say, 50 different documents about different topics and you paste them all into one giant prompt and say, answer this question, the model, our genius, can get overwhelmed. The signal-to-noise ratio just gets completely messed up.
It's like trying to listen to 50 people shouting at you simultaneously. You might hear the loudest voice or maybe the last person who spoke, but you're going to miss all the nuance.
Exactly. So the authors of REPLUG face this dilemma. They have a black box they can't train. They have a context window that is limited and kind of fragile. But they want the model to be able to use massive amounts of external knowledge. They want to give the genius access to a whole library, not just a few pages.
So introduce us to the solution. What is the core intuition behind REPLUG? How do they get around this?
The intuition is decoupling. They separate the system into two distinct players with very different roles. Player one is the reasoning engine. That's the frozen black box like GPT-3. It knows how to speak English, it knows how to code, how to use logic. We treat that as a fixed constant.
That's our genius in the room. We can't change him.
Right. Player two is the memory. This is an external retrieval model. Let's call it the librarian. This is a much smaller, lighter model. And crucially, this is the part we can touch. We can train the librarian to be an expert at finding the perfect document to slide under that door.
Okay, retrieve and plug. We retrieve the info using the librarian and we plug it into the genius. But looking at the paper, the devil is really in the details here. They don't just, paste things in the normal way.
No, they don't. And this is key. The methodology breaks down into two massive workflows. There is the inference workflow, which is what happens when I actually ask a question in real time. And then there's the training workflow, which is how we teach that librarian to be better at its job.
Let's start with the inference part. This is the user experience side of the equation, mechanically speaking. I am a user. I sit down and I type a question. Let's say, what is the primary export of the fictional country of Wakanda? And let's assume the base model doesn't know this offhand, or it's just going to hallucinate. What happens next inside the REPLUG system?
So step one is the hunt. The librarian, the retrieval model, looks at your question. It converts your question into a vector.
A vector. We hear this term all the time. Break that down for us simply.
Think of a vector as just a long string of numbers, like coordinates on a multidimensional map. The librarian takes the meaning of your question, Wakanda, export, economy, and it turns it into a set of coordinates in this, meaning space.
So we're moving from words to pure math.
Right. And the librarian has already done this for millions of documents in its library. Wikipedia, news archives, the pile, whatever. It has turned all those documents into coordinates too. So now its job is just to look for the documents that are mathematically closest to your question's coordinates.
It's looking for a match. Cosine similarity is the technical term, right?
Exactly. It's just measuring the angle between the two vectors. If the angle is small, the concepts are similar. So the librarian runs this search and finds the top 10 documents. Let's say, for the sake of our discussion, it finds the top 10 documents.
Okay. So the librarian comes back to the desk with 10 sheets of paper. I found these 10 things that might be about Wakanda. Now, the old way, the standard RAG way, is to staple those 10 sheets together, put a sticky note on top that says, read this and answer the question, and just shove the whole bundle under the door.
That's concatenation. And as we just discussed, that leads to confusion. Replug says, no, do not staple them.
Hmm.
Instead, Replug creates an ensemble.
An ensemble, that implies a group performance, like a choir rather than a soloist.
That's a great analogy. Or think of it as creating parallel worlds, or parallel timelines. In timeline 1, we take your question plus only document 1. We slide that under the door. In timeline 2, we take your question plus only document 2, and we slide that under the door. We do this 10 times simultaneously.
Wait a minute, let me make sure I'm understanding this. We are actually running the massive, expensive Genius Brain 10 separate times for a single question.
We are, in parallel.
Isn't that incredibly inefficient? I mean, if I'm paying a company like OpenAI or Anthropic per token, I basically just 10x'd my bill for every single query.
Hold that thought on the bill, because you are absolutely right. There is a significant cost trade-off here we have to talk about. But think about the benefit first. In timeline 1, the Genius reads only one document. There is no noise. There is no confusion from conflicting documents. The Genius looks at document 1 and says, based strictly on this text, here's the probability of the next word.
So if document 1 is a recipe for vibranium soup, and document 2 is a history of King T'Challa, the Genius gives two very different answers in those two timelines.
Precisely. In timeline 1, the answer might be soup. In timeline 2, the answer might be vibranium. So now we have 10 different predictions coming out of the locked room. This is the prediction ensemble. We have to somehow combine them into one final answer for the user.
We need a vote.
We need a vote. But, and this is really the secret sauce of the methodology, it is not a democracy. It is a weighted vote.
Weighted by what?
Weighted by the librarian's confidence. Remember, when the librarian found those documents in the first place, it assigned a score to each one. It said, I am 99% sure document 1 is relevant, but I'm only 50% sure about document 10.
Ah, I see. So if the Genius in timeline 1 says the export is vibranium, and the librarian was super confident in document 1, that vote counts for a lot.
Exactly. Replug mathematically combines the probability distributions from all 10 timelines, but it weights them by that retrieval score. This effectively marginalizes out the noise. If 5 of the documents are irrelevant garbage, the librarian hopefully gave them low scores, so the Genius's confused answers from those timelines get mostly ignored in the final tally.
That is a very, very different approach than just hoping the Genius can sort it out themselves. It's forcing focus. It guarantees that the model pays attention to the right information, provided the librarian identified it correctly.
Forcing focus is a great way to put it. It completely bypasses the context window limit because the model never sees more than one document at a time. The context is effectively infinite, limited only by how many parallel passes you are willing to pay for.
Okay, so that's the plug part of Replug. We plug these parallel streams into the black box. But I see a flaw in this plan. A pretty big one, actually.
What's that?
This whole system relies entirely on the librarian being smart. If I ask about Wakanda and the librarian brings me 10 documents about the Muppets, it doesn't matter how many parallel timelines we run. The Genius is going to say, I have no idea. Or it's going to start talking about Kermit the Frog. Garbage in, garbage out.
You have just identified the exact problem that leads to the second half of the paper. Most off-the-shelf retrievers, like the standard Contriever model or even something like BM25, are generic. They are trained on general similarity. They are not tuned for your specific task, or, more importantly, they aren't tuned for your specific genius.
Right. Just because a document looks similar mathematically doesn't mean it actually helps the model answer the question correctly.
Exactly. So we need to train the librarian. But we're back to our original problem. We can't train the black box to tell the librarian what it needs.
We can't open the door.
We can't open the door.
Yeah.
But we can use the black box as a judge.
A judge. Interesting.
This is the most innovative part of the REPLUG methodology, in my opinion. It's called LSR, LM Supervised Retrieval.
Language model supervised. So the frozen genius itself gets involved in the training of the librarian.
Yes, but in a passive, supervisory way. Let's break down the training loop because this is where the real magic happens. Imagine we are in a training simulation. We have a list of questions where we know the answer. We call this the ground truth.
Okay, an example. Question. What is the capital of France? The correct answer is Paris. We know this for a fact.
Right. So step A, the untrained librarian goes out and grabs, say, 20 documents that it thinks are about France. It assigns them scores based on its current, untrained brain.
The librarian is guessing. It's like, here are 20 documents, boss. I think these are good, but I'm not really sure.
Step B, the judge steps in. We take those documents and we feed them to the frozen black box along with the question. And we force the black box to look at the correct answer, Paris.
What do you mean you force it to look at the answer?
We measure perplexity. Perplexity is a fancy term in NLP for surprise. We want to know how surprised the model is by the correct answer, given the document it just read.
Surprise. Okay, let's use an analogy here. Make that concrete for us.
Think of it this way. If I hand you a document that says, Paris is the glorious capital of France, and then I ask, what is the capital? And I show you the word Paris, are you surprised?
No, of course not. I expected that word. It was right there in the text. My surprise level is 0.
Right. Low surprise means low perplexity. That's good. That means the document was helpful. Now, what if I hand you a document that is a recipe for croissants? It mentions France, it mentions flour, but it doesn't mention the capital at all. I ask, what is the capital? And I show you the word Paris. Are you surprised?
I mean, yeah, maybe. The document didn't help me get there at all. I'm just guessing based on my own background knowledge. My surprise is much higher.
Exactly. The model is more surprised than it was with the perfect document. That means higher perplexity.
So the frozen black box is effectively generating a score for every single document based on how easy it made the task. It's saying, document A made the answer obvious, document B was totally useless.
You nailed it. The black box provides the supervision signal. It tells us which documents were actually helpful in reducing its own confusion.
This is brilliant. The genius can't learn, but it can complain. It can say, this document you gave me was garbage and I was very confused by it.
The genius can complain. I love that. Yes, and that complaint is a mathematical value, the KL divergence.
Okay, I promise no heavy math, but we need to touch on KL divergence conceptually because it seems like it's the engine of the learning here. What is it representing?
Conceptually, KL divergence just measures the distance between two different probability distributions. On one hand, we have the distribution from the retriever, which is the list of documents it thought were good. On the other hand, we have the distribution from the language model, which is the list of documents that were actually helpful.
And we want those two lists to match. We want the librarian's opinion to match the genius's experience.
We want to minimize the divergence. We want to close that gap. If the retriever thought the croissant recipe was the best document, so it gave it a high score, but the language model found it useless, which gave it a high perplexity, there is a massive divergence. That is an error signal.
And we use that error to, what? Metaphorically smack the librarian on the nose?
Metaphorically, yes. We use gradient descent to update the weights of the retriever model only. We punish it for ranking the recipe high. We reward it for ranking the geography textbook high.
And you just do this for thousands and thousands of questions.
Thousands. Over and over and over again. Until eventually, the librarian's brain rewires itself to predict exactly what kind of document the genius wants to see.
So the librarian isn't just learning keywords anymore, it is learning something more subtle, like what kind of information actually helps GPT-3 answer questions about history.
Exactly right. It aligns the retrieval logic with the reasoning logic of that specific black box model. It customizes the reading list for that specific brain.
Now, I was reading through the technical notes on this training loop, and I stumbled on something that sounded like a complete logistical nightmare, the asynchronous index update.
Ah, yes. The asynchronous index update. This is the engineering hurdle that kills most of these kinds of retrieval projects in the real world.
Explain it to me. Why is that such a hurdle?
Okay. Imagine your library has 10 million books. To search them quickly, you don't read all 10 million titles every time you have a question. You have a card catalog and index. In the AI world, that index is a massive collection of all the document vectors.
It's the map of the library.
It's the map. But remember, we are actively training the librarian. We are changing the neural network that creates those vectors.
Oh, I see the problem. If the librarian's brain changes, the way it converts the word Paris into a string of numbers changes.
Exactly. The map becomes obsolete instantly. If you update the librarian's weights after every batch of questions, but you don't update the 10 million vectors in the index, the librarian is using an old, wrong map. It will reach for a book on shelf 5 thinking it's about France and find a book about thermodynamics. The whole system breaks down.
But you can't reread 10 million books and update the entire card catalog every 5 seconds. That would take forever.
It would paralyze the training. You spend 99% of your time indexing and only 1% of your time actually learning.
So what does REPLUG do? What's the solution?
They compromise. They use an asynchronous approach. They let the librarian train for, say, 3,000 steps using a slightly stale index. The map is a little blurry, but it works well enough to learn from. Then, every 3,000 steps, They pause the training, and they blast through a massive re-indexing of the whole corpus with a new, smarter librarian.
A periodic refresh, like updating the GPS maps in your car once a month.
Right, it's like updating the card catalog once a week instead of every single minute. It keeps the retrieval pool fresh enough to be effective, without halting the training process constantly. It's a crucial nuts and bolts engineering detail that makes the whole methodology feasible at scale.
Okay, so let's just recap the architecture for a second. First, for inference, when a user asks a question, we use parallel worlds or ensembling to bypass context limits and reduce noise. Second, for training, we use the genius as a judge to supervise the librarian, ensuring we retrieve documents that are genuinely helpful. The big question is, does it actually work? Or is this just some, academic gymnastics?
It works. And the results are actually quite startling, especially when you look at where it works and how well.
Give me the headlines. What were the big wins?
They tested this on the standard GPT-3, the 175 billion parameter version, and also on Codex, the big code model. On language modeling tasks, which is basically just predicting the next word in a complex text, REPLUG improved performance by over 6%.
6%. Okay, for the average listener, that sounds kind of small. I mean, if I got a 6% raise, I'd be happy, but I wouldn't go out and buy a yacht. Why is 6% a big deal here?
That's a fair question. In the world of large language models, perplexity is a logarithmic scale. A 6% improvement on a dataset as massive and diverse as the pile is huge. Companies and research labs spend tens of millions of dollars training larger and larger models just to squeeze out a 1% or 2% gain.
So getting 6% without retraining the big model at all is a massive return on investment.
It's a huge ROI. And it gets even better when you look at hard reasoning tasks. They tested it on MMLU.
MMLU, that's the massive multitask language understanding benchmark, right?
Right. It's basically the bar exam for AI. It has math, history, law, medicine, physics. It's a brutal test of reasoning ability. REPLUG improved Codex's performance on 5-shot MMLU by 5.1%.
Wow, that's a significant jump. That pushes a model like Codex, which is primarily built for code deeper, into the territory of being a general-purpose reasoner.
Exactly. In fact, it pushed the 175B parameter Codex model to perform comparably to models that are much, much larger, like the 540 billion parameter FLAN-PaLM model in certain settings.
So you're making a medium-sized model punch way above its weight class just by giving it better notes to read.
That's the power of context. That's exactly it.
I want to drill down into a specific finding in the paper that really surprised me. They compared REPLUG, which uses a dense retriever, to a more traditional method called BM25.
Ah, the sparse versus dense debate. This is a classic in information retrieval circles.
For the listener, BM25 is basically the algorithm behind CTRL plus F on steroids, right? It just looks for matching words.
It's keyword matching, yeah. If you search for the word apple, it looks for documents with the word apple. We call that sparse retrieval. Dense retrieval is the AI version. It looks for meaning. It knows that Apple can relate to iPhone and also to fruit.
So common wisdom would say the AI version, the dense one, should always be better. It's just smarter.
You would absolutely think so. But the REPLUG paper found something fascinating. They found that an untuned dense retriever, so just taking a standard contriever model off the shelf, was actually worse than the simple keyword search in many cases.
Wait, really? The fancy AI was worse than CTRL plus F? Why?
Yes, because without tuning, the dense retriever gets distracted. It chases these vague conceptual similarities. It might bring back a document that feels like the query but contains no actual facts to answer it. BM25 is dumb, but it's precise. If the keyword isn't in the document, it doesn't retrieve it.
So the AI can sort of hallucinate relevance, in a way.
That's a good way to put it. But, and this is the big but, once they applied the REPLUG LSR training, once they taught the librarian what the genius actually wanted, the dense retriever shot way, way past the keyword search.
So the lesson is, a smart tool is only better if you teach it how to be helpful. Otherwise, you might be better off sticking to simple keywords.
That is a very fair takeaway for anyone building RGAE systems today. Don't just assume vectors are magic. You have to tune them to your specific use case.
I want to ground this whole thing with a story from the paper, the Li-Bai example. I love this because it perfectly illustrates the problem they're solving.
Oh, the Li-Bai example is great. It's all about the long tail of knowledge.
Just set the scene for us.
Okay, so Li-Bai is a very famous Chinese poet from the Tang Dynasty. A generic GPT model has seen his name during its training, so it knows of him, but it doesn't have a deep photographic memory of every detail of his life.
The knowledge is fuzzy, it's there, but it's not sharp.
Right. So in the experiment, they gave the model a sentence about the Tang Dynasty and asked it to predict the next words. The vanilla GPT model was struggling. It assigned a really low probability to the correct historical details about Libai. It was essentially just guessing.
High perplexity. It was surprised by the facts.
Exactly. Then REPLUG stepped in. The librarian went out and retrieved a specific document that explicitly stated Chinese culture flourished during the Tang era. It is considered the greatest age for Chinese poetry.
It brought a cheat sheet.
A perfect cheat sheet.
Yeah.
And because that specific document was in one of the parallel input streams, the model's confidence skyrocketed. The perplexity for the name Libai dropped by something like 15%.
Wow. It went from, I think maybe it's this guy, to, oh, it's definitely Libai.
And this matters because Libai, while famous, is a rare entity compared to, say, George Washington or Beyonce in the massive English internet corpus that these models are trained on.
Right. The model has seen the word Beyonce a billion times. It's seen Libai far fewer times.
Exactly. This proves that REPLUG specifically rescues that long-tail knowledge. It allows the model to access facts that are rare in its training data by pulling them in from the outside, on demand.
It effectively levels the playing field for obscure knowledge. You don't need the model to have memorized the entire encyclopedia if it just knows how to look things up really well.
Which, honestly, is how humans operate, isn't it?
Mm-hmm.
I don't know the GDP of Botswana off the top of my head, but I know how to find it in about 5 seconds. Does that make me stupid?
No.
Yeah, it makes me resourceful. REPLUG makes the AI resourceful.
Okay, we have praised the methodology, we've geeked out on the training loop, but I have to play the skeptic for a minute. There is always a catch. There's no free lunch.
There is always a catch.
We touched on it earlier. The cost, the ensemble strategy.
The elephant in the server room.
If I am running a startup and I decide to implement REPLUG, every time one of my users asks the question, I am effectively running 10 or 20 queries against the GPT-3 API instead of just one.
That is correct.
So that means my latency, the time the user waits for an answer, goes up. My compute bill goes up 10x. Is it worth it?
That is the ultimate trade-off of this entire paper. Computation versus accuracy. Is it worth it? It depends entirely on what you are doing.
Give me a clear yes scenario and a clear no scenario.
No scenario. A casual chatbot for entertainment. If you are building a bot to chat with users about their day or tell jokes, you absolutely do not need REPLUG.
Yeah.
A 6% improvement in perplexity is not worth a 10x bill.
The user won't notice if the joke is 6% funnier, probably.
Exactly. But the yes scenario, a medical diagnostic assistant, or a legal precedent search engine.
High-stakes application.
Extremely high stakes. If you are a doctor asking an AI about a rare interaction between 2 different drugs, you do not care if the answer takes 3 seconds instead of 0.3 seconds. You do not care if the query costs 10 cents instead of 1 cent. You care that it is right.
And you care more than anything that it didn't just make something up.
Exactly. In those domains, the REPLUG methodology is a no-brainer. You are trading cheap compute for invaluable accuracy.
And there's another angle to the cost, right? The comparison isn't just REPLUG versus a standard single query. It's REPLUG versus fine-tuning.
That's the real comparison. That's the one that matters. If you want that level of specialized knowledge, your only other alternative is to buy a massive cluster of A100 GPUs and fine-tune a model yourself. That costs millions of dollars and months of engineering time.
Compared to that, paying a bit more per API call is a total bargain.
It's a massive bargain. It effectively democratizes high-performance, specialized AI. You don't need the supercomputer. You just need a credit card for the API and a really good retrieval system.
It's like a bolt-on turbocharger for the engine you already have access to.
I like that analogy. That's a good one.
We're coming up on time, but I want to zoom out a little bit. We've looked at the mechanics of this. What does a paper like REPLUG signal for the future of AI development?
I think it signals a major shift from model-centric AI to data-centric AI. For the last 5 years, the race has just been make the model bigger, more layers, more parameters.
The Godzilla strategy, just make it bigger.
Yeah, right. But we are hitting diminishing returns on that. REPLUG suggests that maybe the smarter move isn't a bigger brain, but better reading glasses.
Better inputs beat bigger brains.
If you can perfect the retrieval, if you can build the perfect librarian, you don't need the genius to be omniscient. You just need them to be a good processor of information.
It reminds me of that old saying, an education isn't the learning of facts, but the training of the mind to think.
That fits perfectly here. The black box provides the thinking. REPLUG provides the facts.
And I'm stuck on this idea of the AI supervising its own librarian. That feels like a concept that could go to some really interesting places.
Oh, it really raises a provocative thought, doesn't it? If we can supervise a retriever using a frozen LM,
Oh,
could we eventually have a small, cheap, specialized AI that does nothing but learn how to curate the perfect reading list for a giant, expensive AI?
like a sommelier for data.
Ah, sir, for this question about quantum physics, I recommend this vintage 2018 RC's paper with just a dash of a specific Wikipedia article. Exactly. Are we moving toward an era where prompt engineering, which is us humans trying to figure out what to ask, is replaced by automated context curation? A world where the AI figures out what it needs to read to answer you best.
That is a fascinating future. A world where the AI knows what it doesn't know and it knows exactly where to go to find it.
And thanks to this EPLUG methodology, we know it's possible, even if that AI is a black box we can't open.
Unlocking the black box without actually having to open the lock, it's a neat trick.
It's a very neat trick.
Before we wrap up, I just want to summarize that crucial trade-off we discussed one last time, just to make sure it sticks with the listeners. We have this method that really boosts accuracy, but it involves a heavy lift on the engineering side.
Right. It's important to crystallize this. The methodology essentially trades efficiency for effectiveness. On the index building side, the training side, you have the complexity of that asynchronous index update. You are constantly rebuilding your map of the world. That is computationally heavy, and it's complex to engineer properly. Then on the serving side, the inference side, you have the ensemble. You are running 10 parallel API calls instead of one. That is slower, and it's more expensive.
So the trade-off is you pay in complexity during training and you pay in latency and cost during serving.
Yes. But in exchange, you get a model that is smarter, more accurate, and up-to-date without ever having to touch the impossible task of retraining the brain itself.
A high price for a very high reward.
Exactly.
Well, I think we've successfully unpacked REPLUG. We covered the parallel worlds of inference, the judge and librarian training loop, and the heavy lifting of that asynchronous index update.
I think we covered it all, from the high-level intuition to the nuts and bolts.
To everyone listening, thank you for joining us on this deep dive. I want you to think about your own workflows. What black boxes do you deal with in your business or your research? And where might better context be the answer, rather than just trying to force the system to work harder?
Always the right question to ask.
Until next time, keep diving deep.
Bye-bye.